Hi everyone, my name is Fahad Almutairi. I'm postgraduate researcher at University of Leeds. Today I'm going to talk about my project, the effect of composite action degree on RWS connection. In the seismic areas, engineers prefer steel structures because the steel is a ductile material. However, it doesn't guarantee a ductile behavior of the whole structure. Steel structures should be designed to have a sufficient ductility and to avoid undesirable failure, such as formation of plastic hinges on ground level, which would lead to soft story mechanism, basically to make sure the plastic hinges form in the desirable locations. Concerns have raised over the presence of concrete slab and resulting composite actions in jeopardizing the concept of strong column weak beam due to the high strain demand on the bottom flange of the beam. If the composite slab was not considered in the design process. Here we can see on the left side when the high degree of composite actions where the shear studs were placed all along the beam. And the high stress and strain focused on the bottom flange of the beam led to the bolt failure and the flange buckling, as well as a significant cracking of the concrete slab and a moderate amount of concrete crashing around the column. According to the seismic codes in the US and EU, the low degree of composite action where no shear studs placed over the plastic zone and with 25 millimeter gap can be used, which can avoid any cracking and crashing of the concrete slab as we see on the right side. In the last 10 years, there have been a lot of experimental tests and finite element investigation on reduced web section, RWS connection, where the material reduction is happening at the beam web. This connection takes advantage of two concepts, perforated beams to integrate surfaces within the floor to ceiling zone, and the strong column weak beam, which allows for plastic hinges to form around the web opening, which called Farandale mechanism or Farandale bending. It's caused by transferring the shear force across the opening. This mechanism is a good sign as it introduces an additional rotation, which will lead to the increase in the ductility of the joint. The manufacturing process for RWS with multiple openings is similar to perforated beam. They are produced by means of two thermal cut lines in the shape of semicircles. After that, the modules are separated and then welding together. So the height of the new section will be 30 to 60% more than the height of the parent section, or basically creating an opening by cutting the web and then having the same section height. So the advantage of incorporating RWS into the joint, for example, lateral torsional buckling resistance, better than the well-known RBS connection, and easy to cut during seismic rehabilitation. My project is a part of a research campaign led by my supervisor, Dr. Costas, to better understanding of seismic behavior of RWS connection to introduce such connections to seismic design codes. In this campaign, RWS connection were examined with different beam sections, namely European section, UK, and American section as well. Also, RWS connections were studied with and without slab. Experimental tests, finite element investigations were conducted to evaluate the connection performance with a single web opening and fully perforated beam, as we can see here on the left side. It was established that the diameter of the web opening and the end distance play major roles in the seismic performance of RWS connections. The maximum diameter of web opening in literature review is 80% of the steel beam depth, that to ensure the Faraday mechanism to take place. Here we can see the effect of different size of diameter with the same end distance. As the diameter increases, the Faraday mechanism occurs and the stress moving away from the column face. So the distance from the column face to the web center line is a key parameter to gain the full benefit of Faraday mechanism and strong column weak beam mechanism. And as the most of steel moment frames have a concrete slab, here we can see the impact of the concrete slab with and without web opening and with high composite actions. And this indicates that the web opening increases the cracks and the crash of the concrete slab. The aim of this project, which is a part of the research campaign I have talked briefly, to be in the line with the previous efforts and upcoming experimental campaign to promote the use of RWS connection and moment resisting frames in seismic area. Therefore, comprehensive parametric finite element analysis were developed to study the effect of the degree of composite action on the performance of steel concrete composite RWS connections subjected to cyclic loading. Experimental test of Tsavdaridis 2019 was used to develop finite element model, and it was an interior steel concrete composite bolted extended end plate connection with the rib stiffeners, and was designed as a strong column weak beam in accordance with the New Zealand code. Using Abacus software, a combination of 3D shell and 3D solid models were adapted to increase accuracy in simulating the behavior of steel concrete composite bolted connection and decrease the time and computer storage. The load rotation hysteretic curve obtained from the finite element analysis was compared against the one in the experimental test as shown in this figure. The mismatch was compared against the mismatch between the two curves of around 0.3% and 3% in positive and negative maximum capacities respectively. And it was reasonable due to the lack of experimental data on the plastic properties of stiffeners and end plate and bolt as well. The local buckling of beam flanges and concrete cracks were well captured, thus the finite element model was appropriate to employ to conduct the parametric studies of composite RWS connections under cyclic loading. The beam sections that used in the experimental test is a compact sections based on EC3, but it's not a highly ductile seismic sections based on the US seismic codes. Therefore, European beam and column sections were used instead of the New Zealand ones. The equivalent sections have been selected based on geometries, cross-sectional area, and the moment of inertia. The steel concrete composite beam to column joint was redesigned based on EC3 and EC8 to ensure that the strong column weak beam concept was satisfied, and weakening the beam by creating the web opening was used instead of the strengthening the connection by rib stiffeners. So no rib stiffeners were used in the parametric study. The diameter of the web opening equal to 80% of the beam depth, and other two different parameters were used: degree of composite action, both high and low degree, and the end distance. The AISC cyclic loading protocol was selected due to its wide acceptance in the research community. Here we can see the hysteretic curves. It is noticeable that the web opening led to a reduction of moment capacity of the connections as compared to the solid models, as the location of the web openings move away from the connection. The capacity reduction become less. The reduction in the maximum moment capacities the reduction in the maximum moment capacity of models with a high degree was about 1 to 20% compared to the solid model. For the models with a low degree of composite action, in comparison with the solid model, the reduction was around 2 to 41%. RWS connection with a low degree composite action exhibit more stable hysteretic behavior. This was due to elimination of composite action over the plastic zone or the web opening. Similar to the previous studies in this campaign, research campaign and the literature review, the introduction of web opening in the connection can significantly enhance their ductility, provided that the balance between the diameter of the web opening and the end distance is chosen. The use of composite slab affects positively the performance of the RWS connection, providing lateral stability to the beam. The RWS connection with the low composite action have positive effects on the overall performance through reducing cracking and crushing of the concrete as shown in the top figures. Moreover, the stresses and strain were efficiently mobilized away from the connection zone in model with a low degree of composite action. On the other hand, RWS connection with a high composite action, high degree of composite action, which have a severe cracking and moderate crushing of the concrete slab, as well as the greater stresses and strain in the connection and panel zones. To sum up, a composite RWS connection behaves in acceptable manner and provide an ideal structural performance in terms of stress distribution under cyclic loading, provided that a suitable location is chosen for web opening. The composite action should be considered in the design of RWS connection, as it plays a critical role in the ductility. Here are the ongoing projects. The first project is under review, which is a comprehensive finite element investigation on composite RWS connection. The second one is an experimental test on the composite RWS connection as well. Thank you.